Hello everybody, welcome to this video on understanding partial derivatives. Okay, so here's the outline for the video. Part 1, some motivation and setup. In particular, I want to take a look at how surfaces are constructed in 3D, and I'm going to use some Maple to help me along the way. Part 2, I'm going to take a look at some definitions and some of the motivation for the definitions. And finally, part 3, some examples of partial derivatives, and I'm going to do everything from first principles. Okay, so part 1, the general setup. So here's the goal. We want to generalize 2D calculus to higher dimensions. So 2D calculus, we have an independent variable x and some function. We put x into the function, we get some y, and we plot them in the xy plane, we get some curves. So what's next? Well, step up a dimension, we're going to construct some surfaces. So here's the idea. We're going to take some function f from Rn to R. Let's keep things simple. Let's use some domain D, which is some subset of the pairs of real numbers. So these are just x and y numbers, and f. Then we put them in. We get some new number, which will be z. So we have 3 variables: x, y coming from D, and a z coming from the function f. Okay, so how are we going to construct these surfaces? Well, we begin by visualizing some mesh in the xy plane. And at every point in the mesh, we get some height coming from the function, which we're going to plot on the z-axis. So something a bit like this, xy plane, some mesh, as you can see from the colorful plane there. Every point, so I've just highlighted one point in the mesh, I put it into the function, and I've got some height, and we can see from the picture it's just a single point. But if we do this for all the points in our domain, we will get some surface. So that's how we're going to construct our surfaces. This can be extended to high dimensions. We don't have to use pairs of real numbers. We could use R3, R4, so on. Let's keep things simple. We're gonna look at functions from R2 into R, which are generating surfaces. Okay, so here's some examples. Consider the functions from R2 into R. There's 2 of them. The first one, it takes some point in the mesh xy, it's in the xy plane, and the height is x squared plus y squared. So let's take a look at this one. And whilst we're here, we might as well look at another. What if we, instead of add, we subtract? So x squared, take away y squared. Okay, so it's a bit harder to draw, so we can use Maple. If we go to Maple and we use the plot 3D command, so we do plot 3D, type your function, so on the left, x squared plus y squared, and hit enter. We get that surface. And similarly, if you plot 3D x squared minus y squared, hit enter, you get the surface on the right. Okay, and Maple's a very nice program. It's very good at telling us what scales look best. So I picked some x and y's, and then it chose the heights to make the pictures just look nice and scalable. Okay, so there's some surfaces using some of the ideas I discussed earlier. So next, part 2, how can we study change whilst moving over some surface? Okay, so I'm going to pick a different function. I'm going to ask that question of how to measure change for f, and this function it takes some mesh point xy and it produces x e to the power x squared plus y squared. Okay, so where would you start to understand the change in this function f? A good place might be Maple. If we go to Maple and use the plot 3D command, type in the function x times e to the power x squared plus y squared, pick some x and y values. I've chosen 2 to -2 for both of those variables, and we generate the following surface. Okay, so quite interesting surface. It's quite clear actually. There's lots of colors in there. We can see all the contours. So how does this change? How can we quantify change for this function, or more broadly, any function from R2 to R? Well, here's the approach. This is the way that we do it. We study changes in the function f by, well, firstly, by fixing the y variable. Okay, so we pick some number for y, and we say, right, don't change it, that's fixed. And then we move in the same direction as the x-axis. Okay, this gives us some idea how the surface changes, moving in some predetermined direction. Okay, so that's one way of studying the change. We could fix the y, move in the x direction. We could also do the opposite. We could fix the x variable and then move in the direction of the y-axis. We get some idea about how the surface changes, moving 90 degrees, so either along the x-axis or the y-axis. So this is the approach we're going to take. Okay, so let's pick some value. I'm going to fix my y. I'm going to choose 0. So go to your surface and say, right, I'm going to put y as 0 and I'm going to move in the same direction as the x-axis. Well, it's a little difficult to do looking at the screen. So what I've done is I've drawn in a vertical plane. The vertical plane, it's going through it's going through the point y equals 0. And as we can see, it's parallel to the x-axis. Every point on that plane has a y value of 0. Okay, so if you're on the surface and y is 0, and then try to imagine moving along the surface. So it's the intersection of f, the surface coming from f, and that plane. Okay, we can do a bit better than this. This is quite hard to visualize. We can go to our function. We can put y equal to 0. So if I go back one, here's our function f. If we put y as 0, well, that is just x e to the x squared. So the intersection of the plane and the surface, x e to the x squared. So we can plot that. So effectively, moving along the surface is, while staying in that plane, it's just the same as this graph, which is x e to the x squared. Okay, so that's how the surface changes moving in this direction. And that's great news. So why is that great news, you might ask? Well, this now is a two-dimensional problem. We have a curve and we want to study how that curve changes. We can use all the ideas from 2D calculus to do that. What I mean by that is we can fix our x point. Y is already fixed, so we have our mesh point, and we can draw a tangent line in the plane on the surface, which is just the same as this graph, and we can measure the slope of the tangent line, get some idea of how the surface is changing in this particular direction. Okay, so all of this then motivates the definition of partial differentiation. So here's the formal definition. There's two calculations we can use to study change. So same setup as before. fxy, this is controlling the height. The first order partial derivatives of the function f. Let's deal with the top line. F subscript x just means the partial derivative of f with respect to x. It's just a shorthand. And the definition is we take the limit as h goes to 0. The y's are fixed. We can see in the function, those y's don't change. But the x's do move. We change from x to x plus h. So we're moving along that plane, along the surface, and we're dividing by h, taking the limit as h goes to 0 to give us the gradient of the slope as we move along the surface in the plane with fixed y value. Okay, so that's the partial derivative in the x direction, y fixed. We go down to the second line, very similar. F subscript y is the partial derivative of f with respect to y. So the x value is fixed and we're only moving in the direction of y. So we pick some y, we move along a little to y plus h, we evaluate at the function, subtract, divide by h, and then set the limit to 0. And this is going to give the gradient of the tangent as we move along the surface in the direction of the y-axis. Okay, so there's a few things to take in there. Something that can be done with just a bit of thought. Go at your own pace, go comfortable pace. Next, let's take a look at some examples. Some examples using first principles. Okay, so let's revisit f of xy equals x squared plus y squared. We know the partial derivative of f with respect to f is the following limit. Okay, now we have a function to work with. So f of x plus h, y. We replace x by x plus h. So we're going to square x plus h plus y squared. Then we're going to subtract f xy. Okay, we've got that. Divide by h and take the limit. So let's do it. Okay, so we have some brackets to square out. Okay, so just a bit of simple expansion of brackets. And what do we see? Okay, we can see the x squareds are going to cancel. The y squareds are going to cancel. We have h in the 2xh and in the h squared, they're going to cancel with the h on the bottom. So what we're left with is 2x plus h as h goes to 0. So the partial derivative of f with respect to x for this function is 2x. Okay, great. So there's our first example. Does it make sense? Well, we'll see that in a moment. Before we start to investigate, does this make sense? We should think about what we've just done. Well, this calculation is identical to the two-dimensional case, y equals x squared plus some constant, which is studied at A-level, at high school. It's exactly the same calculation. So the point here is we don't need to keep using first principles. Instead, we can use all our knowledge of two-dimensional differentiation, and wherever we see a y, we just think about it as some fixed number. Okay, so in our function, we have a y squared. If y is just some constant, you square it, it's just a constant. So we're differentiating x squared plus c some constant with respect to x is 2x. That's exactly what we're seeing using this principle. The derivative is 2x. So there's not a lot of new ideas here in terms of doing the differentiation. You can very much rely on things you've studied in high school, which is great news. Okay, does it make sense, our solution? The derivative in the x direction is 2x. Well, let's pick some y number. So we said y is fixed. Let's pick let's say 2, y equals 2. So move along the surface in the direction of the x-axis, where y is always 2. Well, again, it's a little hard to visualize, so I'm going to draw the vertical plane that goes through y equals 2, and then move along the intersection with that surface. What can you see? Well, it looks a little bit like a parabola, and we can confirm this by just putting y equals 2 into f. We get x squared plus 4. So yeah, it is a parabola. It's x squared plus 4. If we differentiate that with respect to x, we get 2x, and this is exactly what we calculated. The partial derivative of f with respect to x was also 2x. So yes, it makes sense. Everything is tying back to 2 dimensions, which is great news. Okay, so that's a good point to end this video. I hope you find it useful. Lots and lots of helpful examples to follow. Hope you enjoyed.